electric cabin. Rocket in the night.
I think it's an example of the kind of systems that people are building now, which take advantage of the tremendous versatility of computer systems. We can do things with computer systems that we wouldn't dream of doing with mechanical systems. No one would have built this system in hardware. It would have been far too complicated and far too physically error-prone.
Increasingly complicated computer control systems are being used in safety-critical situations, where people's lives may be at risk if there's a computer error. But the financial benefits of computer control are enormous. These trains have no drivers. They run automatically a few minutes apart along some 15 miles of track. The whole thing is controlled, of course, by computer. And the train captain is here on board simply to look after things and to check the tickets. Every day, thousands of commuters and tourists travel on these trains. Their safety depends on the smooth running of the computer control system. This railway is an intrinsic development in the regeneration of 8.5 square miles of real estate. London's Docklands is Europe's largest building site. Progressively abandoned since the 1960s as the container ships docked downriver at deeper ports, it's been an eyesore for years. With the 1980s came redevelopment, offices and residential areas. But close as the Docklands were to the crowded city, there were no rail links to bring the commuters in. So in 1987, the Docklands Light Railway was opened. The combination of light railway technology and a computer control system kept costs within the strict government cash limits. And already it's being expanded, partly funded by private finance from developers. Light railway technology essentially means small, light carriages which can turn tighter corners, accelerate faster, and stop quickly if necessary. Tighter curves mean less real estate, and lighter carriages need less expensive railway structures to support the tracks. And the final reduction of costs comes from the computer control system. Whole sections of individual job descriptions of driver, guard, station manager, ticket inspector, and signalman are all undertaken by the computer system. One of the key jobs which still requires human supervision is door closing, which no computer is yet sensitive enough to carry out safely and efficiently. Well, that train is now on its way to Stratford, and it will be watched at every step of the way from over there, watched by the computers in the main control room. This is the Operations and Maintenance Centre, the heart of the automatic train supervision. Here, the computer monitors train movements, dispatches trains, and regulates them according to which of its stored timetables is in operation. It displays which sections of the track are clear and which trains are at which station. And the controller can keep in human touch with the train captains at all times.
Transit 0420, base over. Transit 04, yeah, John. When you get to Tower Gateway, I want you to do me one small favour. Can you check the escalators for me?
Over.
Received and understood, over.
Right to receive, thanks now.
Train departing platform 1 is for Tower Gateway.
Platform announcements and indicator boards are automatically triggered by the computer. and it even counts ticket sales. A sophisticated control system must keep track of its own faults. There's even automatic compensation for small irregularities in the timetable by adjusting the time spent in the station or by varying the speed of the train along the track. Each train has its own on-board computer, which is programmed to drive it around the network. And at each station, there's a communications box, physically linked to the control room. As the train arrives, it comes to a stop over the link to exchange information. It transmits which train it is and its destination, which the main computer confirms, and gives the doors on the correct side the signal to open. It's at this stage that the timetable irregularities can be made good. Between the stations, the onboard computer is on its own, accelerating, coasting and braking to a predetermined pattern. It keeps track of how far it is to the next station by counting its wheel turns as it goes, and checks this by referring to loops in the central wire. But computer control systems cannot run unchecked, and a second, separate onboard system has two specific safety tasks. It checks that the speed is appropriate for the location, and picks up a safety tone from the rails that there is no train ahead. If there are problems, it stops the train. In addition, if there is any mechanical or software failure, it also stops the train.
To drive the train, it is fairly complicated. But the important thing about the system is that to protect the train and the safety side of the system, it's a very simple system.
Simple because there are basically only three dangerous situations it has to look out for: overspeeding, another train, and a system failure. When one of these events happens, it fails safe. It stops the train. Most importantly, the train can then be driven by the captain, with no need for the computer at all if necessary.
Train departing platform 2 is for Stratford.
The Docklands Light Railway is the first of this particular system in operation, and as such had its share of problems. The system was extensively tested prior to going into service, but of course, once passengers start to ride, the software may need adjustment, or it may come up with unexpected errors. On the official opening day, the computer wasn't driving the train.
Well, actually, what happened was that the royal party had arrived quite early, and we only had one royal train operating that day, so we'd programmed into the central computer, the operations and maintenance centre, a special timetable for the royal train. When the train, because the royal party arrived early, the train actually was ahead of its schedule, and it was given a manual departure. Now, when it got to the next station, it was still ahead of schedule and didn't depart automatically. So the train captain on the train was a little bit confused and thought there was a fault, so he took the decision to drive manually from there.
The press took it up, didn't they?
They did, yes.
What did they make of it?
Well, they were at the time still saying that there was a lot of problems with Docklands Light Railway, and they felt that that was one of them. But it wasn't actually really a fault. It was just the fact that the thing was ahead of schedule.
But people do worry about computer failure. Is there a hidden software error that could cause an accident? What if the train doesn't stop at the station? What if the doors don't open? What if it goes too fast? So a major problem in designing any automatic control system is in thinking of all the possible things that could go wrong and making sure that those things cannot happen. It's that initial thinking process which is vital in a safety-critical system. And the intellectual problems multiply as systems become more complicated. There were thousands of lines of computer instructions controlling the train system. An aircraft system needs millions. How reliable is it? And what happens if it goes wrong? An aeroplane can't simply stop. This is the A320 Airbus, which first joined the fleet of Air France in April 1988. It's the first commercial plane to use the fly-by-wire system. That is, it's the first non-military aircraft to rely on software to control the movement of the plane. We've had computers and autopilots in planes for many years now, but this system is quite different. Instead of heavy mechanical linkages from the cockpit to all flying surfaces, there are just thin wires which carry an electrical signal from a computer. So effectively, the pilot is flying the computer, not the plane. The advanced computer system on this plane means that passenger costs are substantially lower than for any other commercial aircraft. This is the cockpit of the future as far as commercial aircraft are concerned. Gone are the large central pedestals, the equivalent of the steering wheels, and in their place are small side sticks. Gone also are most of the mechanical links to the flying surfaces. Gone are the mechanical dials and indicators, and in their place, computer screens. But the innovations are not simply in the cockpit. The very shape of the plane is new, with thinner wings at more of an angle to the body, which allow more efficient flying. These design changes are possible only because of the computer. Power and control surface settings have to be set with the precision only a computer can give. There must be no extraordinary strain on what is inherently a more fragile structure than ever before.
Ok, démarrage est terminé.
Avion dégagé. Est-ce que ça peut passer à droite, s'il vous plaît?
This is a plane that pilots like to fly. Most of the lengthy calculations and plotting are done automatically. Once a month, updated information covering an area from Iceland to North Africa is loaded into the computer navigation system. This includes height and direction of airport runways, radio frequencies and so on. Then, once an aircraft knows where it started, it will know wherever it is thereafter by checking its own internal gyroscopes and checking with en route beacons.
On the primary flight display, you have the speed scale with here at the blue dot the instant speed, and here in the red part of the scale the forbidden speed. We must not go in this part of the speed because this may damage the aircraft. We have right here at the green dot the olden speed. This is the speed at which fuel consumption is the best.
When we make a choice for an aircraft, we make a choice for an aircraft for the pleasure or the comfort of our passengers, for the economy of the airline. Don't forget this aircraft makes 40% of economy comparatively to the B727 comparatively. But for me, I'm an engineer, I make a choice for the high level of technology of this aircraft.
I think it is a big improvement in safety to have all display as we have today and warnings, because with such displays, such computers, you have the possibility to have good warnings. And instead of hundreds of instruments, lines, something like that, you have pages, you have a central alarm system.
On this flight, the all-important black box was not operating. Also, the automatic cabin pressure was faulty, an ongoing software fault that by the end of 1988 was still not solved. But more controversially, the computer has a veto over the pilot. Any commands it deems inappropriate are ignored. It knows what commands could overstress the plane's structure. This means really that you can't do anything stupid, does it?
Sorry?
This means that you, as the pilot, can't do anything stupid. The computer would look after you.
They help me, they help us. But this is very useful for us.
I think they've decided in this aircraft to go for a fairly fancy computer system, and it provides all kinds of wonderful facilities. It stops the plane stalling, stops the pilot doing certain crazy things that pilots occasionally do, damaging the aircraft, for instance. All of that's to the good. On the other hand, they've taken a secondary decision, which is to save weight by not having a full mechanical reversion. So if the computer system should be lost completely, the pilot has only a vestigial mechanical backup. Now, those seem to me separate decisions. The first one, providing these fancy facilities, is a good decision. The second one, I think, is more questionable.
But how likely is the computer system to fail anyway?
I think one of the difficulties is that Airbus set themselves an extraordinary objective. They're on record as saying that they wanted the reliability of this system to be a failure rate of 10 to the minus 9 per hour. And let me explain that. That says that they want a system that will fail only once every billion hours. Now, a billion hours is 100,000 years. Now, that's an extraordinary objective, and they stated that as their requirement. I think anyone in their right minds would not hope to achieve it, and I would certainly not trust anyone who said they had achieved it.
But how could you make that claim?
With difficulty.
Obviously, the question arises, what happens if the computer goes wrong, as indeed they do sometimes?
Well, we have several computers, and in case of failure of 1 or 2 or 3, for flight control we have 5 main computers used for the control, and it is quite impossible to lose 5 computers.
Each type of equipment, the 2 computers from aileron on one side and the 3 computers for spoiler on the other side, are made by 2 different manufacturers, each of them involving team for software, which of course are different. So we have a complete separation on the type of control in 2 different ways for this axis. And it's the same for the pitch, is the same for the other flight control.
This is what's called a fault-tolerant system. 5 computers and 2 different software systems in case of errors.
It seems impossible that the 2 software will be including the same type of error, because the way that they are built, the starting point, the different sequence are different. It is impossible.
He says it's impossible? Well, that's nonsense. I mean, there's plenty of scientific evidence. There's theoretical evidence and empirical evidence. People have done experiments, and there are plenty of cases, plenty of evidence to suggest that that just is not true. For instance, there was an experiment done in the US where 27 versions of a particular program were written independently, and many common faults were found. People making the same intellectual mistake. And it comes back to this problem of the whole difficulty being intellectual problem solving. And we have common cultural backgrounds. We tend to make the same mistakes. And there are theoretical reasons why you would expect even independent, truly independently written software to contain common faults.
Decision height is 200 feet. Decision height.
Most pilots would agree that the critical time for a plane is on landing. This system can do everything automatically.
And I check the next phase, which is the go-around phase, in case we would have to perform a go-around or a missed approach, for example. So the computer is now programmed. The aircraft should be able to do it automatically until the aircraft is stopped on the runway without any pilot's action.
Okay, Varia. So my friend has selected the flaps to 1 position.
But if the same software fault came up on both software systems, could the plane be landed without the computers?
Without any electricity on board, without any help of computer, you assume the landing. This was made already in demonstration by the flight pilot from Airbus industry. Of course, it's not the current way to land in Air France with this type of aircraft.
It can be done.
It has been demonstrated 3 times.
That surprises me. My understanding was that they hadn't actually done a full mechanical landing. Is he saying that totally without the computer system, using only trim and rudder, that it's been landed?
As I understand it.
I'm surprised, but I would be even more surprised if any airline pilots had attempted such a thing. Are the airlines, for example, training their pilots to do that?
Have you ever had to do that?
Not me, especially not me, but it has been experienced during the certification phases.
How confident are you that your pilots could do that? Because obviously, as you say, they are not trained to do that.
That's true. That's true. And it's a question which is under evaluation to see if at the level of the simulator, for example, it will be not possible to demonstrate. For the time being, there is no training involved on that. But I repeat, this was already demonstrated by Airbus and A320 pilots.
This is the circular argument. The computers will not fail because there are 5 of them. Anyway, if they do fail, the plane can be landed manually. This is not part of the training for pilots because the computers will not fail. The possible reluctance of the manufacturer to encourage manual flying may be due to their future plans. Future aircraft will be designed aerodynamically unstable, and without a computer there is no question they simply will not fly.
20, retard, 5.
As with the Docklands Railway, there were public questions about the safety of the software. In June 1988, the A320 crashed.
The computer system is supposed to fly the aircraft close to stall, safely close to stall, and it demonstrates it beautifully by coming in at 30 feet with the nose up like that, slats and flaps deployed, and the wheels down.
What went wrong?
It's difficult to say. All the news reports seem to suggest that the thing was flying at 30 feet quite safely, and it hit trees at 40 feet.
But within hours, the announcement came that this was a human, not computer error. To enable the plane to fly so low, the pilot had had to switch off the height monitoring computer.
I'd like to be able to predict how reliable it will be in service, how safe it will be in service. And the problem is, and the central problem from my point of view, given my research interests, is that no one seems to have measured that. So we simply don't know how good that control system is.
How confident are you in it? Would you fly it?
I prefer not to, but I must confess that I took my wife and kids on a DC-10 shortly after the DC-10 crashes, so I guess I would. I think Airbus have shown a pretty good record so far. I'm sure they've done the best they could to build a safe system. It just worries me that the demands on this system appear to be very great. It needs to be very reliable, and no one's measured how reliable it is.
There is no authoritative source of data on the number of safety-critical systems in use or under development, and therefore no public record of their complexity or failure rate.